We've done everything.
That's fine.
I know.
All
right. Good morning, ladies and gentlemen, and welcome to, I think it's Wednesday. We've got just a few notes that we're going to cover today, and then I'm going to give you a worksheet that we are going to work on together. Whatever we do not get done is what you will work on this evening. Okay? So, as I mentioned, as you're getting your notes out, we'll be talking about just recap again what we've been doing over the last couple of days, and that is electron configuration. And we are going to continue electron configuration in today's topic. But as I've stated before, we're going to take it a step further, and we are going to demonstrate through another visual tool where electrons are placed. This time, however, we are going to apply a couple of different rules for when we create what are called orbital block diagrams. And so, with those rules, we're going to I'll try to put them in simplified terms so they make a little more sense, because some of these can be technical. And then we'll put to practice, okay? So, orbital box diagrams are simply just built off of electron configurations, okay? We have three rules that govern orbital box diagrams. We have first called the Offbound Principle. We have second the Pauli exclusion principle. And then third, we have what's called Hund's rule. Okay? Again, putting all three of these together and keeping them in mind, they define how the electrons can be arranged in an atom's orbitals. And these three are not terribly difficult to put them into practice, okay? Because when we do some examples and we get started in your homework, we're going to show you, again, just like electron diagrams or electron configurations, they too follow a pattern. Okay. So let's talk about the Offbound Principle. The Offbound Principle simply states that each electron occupies the lowest energy orbital available. So they're not. If you start placing electrons into orbitals, you're not going to start at the highest energy level. Okay, that's just not cool. Atoms do not like to have their electrons in high energy. Goes back to the underlying theme of stability. Okay, so we always try to fill in lower energy orbitals first. They go from lowest to highest. So, sub-rules related to the Offbound Principle. Okay? All orbitals related to an energy sublevel are of equal energy. And what that means is, we stated early in this chapter that the p orbitals are made up of three separate orbitals. Okay? All three of those orbitals that make up a p orbital are of equal energy. But when we get into what we call a multi-electron atom, which is essentially any element not hydrogen, so every other element except hydrogen, the energy sublevels within a principal energy level have different energies. For example, when we get into row 2, okay, where we have 2s and 2p, okay, the 2p orbitals have higher energy than 2s. That's why when we did the electron configurations, we always listed the s first, because what we're essentially doing in the electron configuration is placing electrons in increasing order of increasing energy. Speaking of increasing energy, there is an order in terms of the 4 orbital types. In that order, in increasing energy, is S, then P, then D, then F. So F is its highest energy orbital. And then this last statement, statement D here, addresses why we have situations when we get into the D and the F orbitals, when we have to drop that N value down. Like we were in 4s2, then we go to 3d10, okay? The reason why we have that difference in our numbers is because orbitals related to energy sublevels within the same principal energy level, so within that same 4th principal energy level, they can overlap. That's why we get the situation where we have 4s and 3d. That 4s is actually lower in energy than the 3d orbital, but they can overlap each other. That's why we have that kind of drop in those N values. Next is the Pauli exclusion principle. This states that a maximum of 2 electrons can occupy a single orbital, but only if the electrons have, and this is very important, opposite spins. If you look at this image in the bottom right corner of your slide, we represent the spins of the electrons using arrows. We have an up arrow, which simply just represents the electron spinning in one direction, and a down arrow representing the spin in the opposite direction. When you have orbitals that have paired electrons, you'll have one box with one up arrow and one box with one down arrow. What that does, by having individual boxes with shared electrons with opposite spins, this will eventually reduce some energy and allow them to remain in that same orbital box. Now, staying on the same slide, I've got a pop quiz for you. Looking at this image right here, can anybody tell me what orbital this is representing? Will I see you thinking? Okay, there are 3 orbitals, and so what orbital type has 3 orbitals? Not S. P. Yes. Another way you can do it is count the arrows. How many arrows do you see up here? 6. What orbital can hold a max of 6? Okay, so another thing I want to address here is, like Will said, Will counted 3 boxes, right? Each box represents an orbital. 3 boxes total. There are 3 p orbitals, so that's p. Okay, continue with the pop quiz. How many boxes would you make for the d orbital? Who said that? Perfect. 5. There are 5 orbitals in the d orbital. And so what's the max number the d orbitals can hold? 10. Awesome. Okay, what about F? 7. Very good. So you have 7 boxes for the F orbital. And they hold a max of how many? 14. Awesome. And last one, S. How many boxes are you going to have for S? Awesome. 1. With the max number of electrons of, perfect, 2. Excellent. See, you're already ahead of the game with this. Okay? So, one last thing we got to talk about is Hund's rule. Now, I'm going to state this Hund's rule, then I'm going to kind of hopefully relate to something that might be familiar to you. Okay? Hund's rule states that single electrons with the same spin must occupy an equal energy orbital before any additional electrons with the opposite spins can occupy that same energy level orbital. And this is because negatively charged electrons repel each other. So if you have negatively charged electrons with opposite spins, they tend to repel less. Okay. So here's an example. If we are constructing an orbital box diagram, and we are trying to fill a 2p orbital. So we're trying to fill, if you look here, we're trying to fill the neon 2p orbital. Okay. Neon is going to have how many electrons in the p orbital? Anybody take a guess? Right here. If you look over at the periodic table, what's the number I'm going to put on the p orbital right here? 6. Okay, so I have to put 6 electrons, or in this case, 6 arrows representing the electrons in a box. And so there are 6 steps as shown here. Can anybody identify what's happening? Do you notice a trend happening in the first 3? Maddie, what is it? All right. So as you see here, we have 3 boxes that we said is for the p orbitals. We start placing the electrons or the arrows in here. You notice that the first 3 electrons we place are the same spin or same direction. And by general rule of thumb, we always start with an up arrow. Okay. But you also notice that each of the boxes gets an up arrow before we begin doubling up. So here on the 3rd step, all 3 boxes have an up arrow. So now that we can start doubling up, you notice when we double up, we have the opposite direction arrow. Now, I like to relate this to family gatherings, okay? You're at a family gathering, and you have a large spread of food. Everybody has an empty plate. But today, Tristan is super hungry. Okay? So Tristan hops in line, gets a plate of food. Okay? He takes it back to the table. He scarfs it down. Tristan isn't full yet. So Tristan gets back in line. But this time, Tristan butts people who haven't got a first plate yet. Do you think that people waiting in line to get their first plate are going to be thrilled with what Tristan did? What do you think, Tristan? No. And so one thing you want to keep in mind is imagine that each box is kind of like a plate. Okay? And you're at a buffet. They're handing out electrons. Every box or every plate has to have 1 electron before you can go back for doubles. Okay? So this orbital, this p orbital, has 3 plates. So each plate has to have an electron in the same direction before you can go back for seconds. Okay? So I also call this the Hungry Huns rule. Have you ever heard of Hungry Hippos? A few of you? Okay. Get less every year. That's the entertainment we had growing up as kids, those little plastic hippos that we had to smack and eat little plastic foods. So little plastic marbles, yeah. So yeah, technology's come a long way since then. Anyway, so those are the 3 rules that we are going to keep in mind when we do orbital box diagrams. And so here is the process of drawing orbital box diagrams. First, you don't have to, okay? So when we do some of our examples, I'm going to show you both methods, okay? This says to write out the noble gas electron configuration for the element, okay? Because honestly, when you start doing orbital box diagrams, they're going to be even larger in size than your electron configurations because you have to include more images in there, okay? So for each of the subshell, whether it be 1s, 2s, 2p, so on and so forth, yada, 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 you have to draw the orbital boxes. Underneath the orbital boxes, you must then write the name of the subshell, which again is 1s, 2s, 2p, so on and so forth. You will then place the arrows that represent the electrons into the orbital boxes following Hund's rule. Okay. So let's look at a couple of examples here. Okay. First, we have silicone. That's the wrong marker. Next, we have fluorine. And then lastly, we have calcium. Okay. So, okay. All right. So, let's start with silicone. Okay. I'm going to brighten this up a little bit. All right. So silicone. Can anybody find silicone on the periodic table? Where is it, David? Right there. Don't mind my shaky hands. It's coffee. Okay, right there. Even though the directions say go ahead and do the shorthand version, it's not that far from our home base. So let's do a practice one with the longhand version. And then we're going to do the orbital box diagram associated with it. Let me get the chair. Okay. So where do we start? Doing the longhand version. What element? Hydrogen. Okay. So let's proceed here. We start at hydrogen. We go all the way to helium. So we got 1s2. We then are at the end of the row. We go down. We're in row 2. 2s2. Hop across the pond. We get to 2p. We're still not at our destination yet. So we count. We continue going on. 2p6. So we're at neon right now. We then come to the end of a row. We hop down and all the way to the left. We're at 3s2. And then 3p6. Oh, no. Sorry. 3p2. I don't know what I was thinking. Okay, so there's your electron configuration. Now we do our orbital box diagrams. And so what we're going to do now is first draw boxes. Now you can draw boxes or you can draw a line to represent a box. It is up to you. I personally like to do boxes. It's your own prerogative, okay? So we start here when we construct our orbital box diagram. We start here on the left of our electron configuration and identify the orbitals that we have to use. So our first orbital is S. So we, again, there's one box, okay? And beneath that, we just write 1s. We do not write that superscript of 2 on there because we're going to use the arrows to represent that 2 right there, okay? So there's my one box for 1s. How many boxes am I going to draw for 2s? Draw 1. Again, I'm only concerned about the orbital. Okay, so one box for S. So I've got 1s and 2s. How many boxes am I going to draw for P? 3. Again, you can just do it this way. Draw a big rectangle. Do that. And then below that, you label as 2p. And I still need to do a couple more boxes here. I come into another s orbital. How many boxes do I draw for that s orbital? 1. Very good. And so it gets a label of 3s. And then we're on another p. So again, we draw 3 boxes, label as 3p. Okay. So we should have the correct number of boxes for each orbital as well as the label beneath it. So we are going to start placing in electrons. Now, as we go through this, I'm going to kind of be talking a little bit. How many electrons do I need to put in this first box? 2. Up arrow, down arrow. I cannot go on to the next orbital until I have completely filled in the previous orbital. And so I've done just that. Okay, then I hop over into 2s. How many electrons go here? 2, again. 1 up arrow, 1 down arrow. Now I get into 2p. How many electrons have to go into this whole orbital? 6. And how many arrows go into each box? 2. Now, this is good practice here, okay? We're going to follow Hund's rule, where every plate or every box on here has to get an arrow in the same direction first. So I have 6 electrons that need to be dealt with. So what I do, if you could draw a better arrow than I can, feel free, because that's terrible. Okay, draw an up arrow in that box, an up arrow in that box, and an up arrow in that box. Now, can I go ahead and start doing 3s? Why not? Yeah, I have to complete this orbital first before I can move on. And so, Tristan, how do I complete these boxes? Yeah, I got to put down arrows in there, because now everybody in this orbital has an arrow. You can go back for seconds. So they each get a down arrow. I've placed 6 arrows in this orbital. And so that is complete. Then I hop over to 3s. How many electrons do I put in here? 2. Very good. 1 up arrow, 1 down arrow. Now, this brings me to 3p. Okay, how many electrons do I have to deal with here? 2. I know that because I put a 2 here. And so, don't write this, okay? What I cannot do is this. I cannot do that. That disobeys Hund's rule. Again, Hund's rule, everybody has to have one that can have one. So, you get a result like this, okay? Even if it doesn't fill up with all 3 boxes with an arrow, you still each get a single arrow. And the reason is this. Going back to Hund's technical definition, by placing these arrows in the same direction, we actually minimize the overall energy. If we tried to place a down arrow for our second electron here, we would place the electrons close together and would result in higher energy, which is a no-no. Okay? So by doing this way, having 2 arrows in the same direction in different boxes, we actually reduce energy. Okay? Let's do fluorine. Okay? Fluorine is number 9 right here. Okay? Again, it's a short one. So, excuse me. We'll go ahead and do the longhand version again, just for extra practice. For the last one, we'll do the shorthand version, okay? So starting with the longhand version, we start at hydrogen. We go 1s2. What's next? 2s2. What's next? Very good. 2p5. Okay. Now, we've got this. Let's set up our boxes. Again, how many boxes do I need for this S here? 1. Very good. Label it 1s. How many boxes do I need for this S here? 1. Awesome. Again, label it there. How many boxes do I need for P? 3. Awesome. You're doing awesome. Label it 2p. Okay. How many electrons go in this first box? 2. 1 up, 1 down. What about 2s? 1 up, 1 down. Now for P, we have 5 electrons we have to deal with. So tell me if I follow Hund's rule correctly. Did I follow Hund's rule correctly? I did. Because before, I made sure that each box had an up arrow before I went back for seconds. So this poor little electron's all by itself, which is fun. So next, if I can get some room here, is calcium. I told you we'd do the shorthand version here, okay? So, locate calcium on the periodic table. Right there, right? So, let's do the noble gas or shorthand configuration. What noble gas am I going to use? Argon. Again, in order to determine which one we use, we locate the element, and then we go up a row and all the way to the right. So that is argon. And again, when we do this, we place the symbol for the utilized noble gas in brackets, and that now becomes our new starting point. Okay? So we're starting from here, and we need to get here. So what do I write here first? Will? 4S2. And that's it. Okay? Again, it's a very simple one to do for these orbital diagrams, but hey, it's still doable. So this time when we do this, we follow the same procedure, except this time we rewrite the noble gas that is used, and then we follow it up with the boxes that are needed. So how many boxes do I need for this one? And again, you label it appropriately. How many electrons go in here? 2. 1 up, 1 down. Questions on orbital box diagrams? Okay. I'm going to hand out this worksheet. I want you to bring into class tomorrow. Okay? Again, we will go over this together, but I will be doing the same procedure in calling out names. Okay? Make sure you put your name on this. Don't lose it. And again, before we go on to the next section, I have to make sure that we are okay with this. The third part of this section is actually pretty simple. All right, so as you see here, for each element, there are 6 elements here, do the electron configuration. For most of these, or actually for all of them, they do have it set up to where they've got the orbital box diagram starter for you. Again, instead of boxes, they just use lines, which you can do it right above those lines. However, I do want to mention a couple of these because they're not set up as nicely. All right, if you go down to number 4 for germanium, okay? Germanium does not have enough lines. So to the right where it says 3D, you'll want to put 4P, and if you want to continue the trend, just do it outside of 3D, okay? That's for germanium. Same thing for krypton. Just to the right of 3D, you'll want to put 4P and 3 lines above that as well. Now for number 6. Number 6, go ahead and do a couple things. A, you can use the noble gas configuration. Okay. And B, cross out what they have already for you in terms of the box diagrams. Okay, cross that out and make your own because they are not labeled correctly. Okay. So again, for number 6, do the noble gas configuration and draw your own boxes or lines if you choose to do that. Okay. And again, we will convene first thing tomorrow in class and go over this before handing it in. Okay. So if you want to try the first one, go ahead. You got a few minutes left in class. Yes, ma'am.